Okay, perfect. So let me start by thanking Nicolo, and Marco for giving me the chance to present some of my recent work in this very nice seminar series. So in this talk, I will present some universal pattern that we found in quantum gravity together with Inés Valenzuela and Ignacio Ruiz. And these patterns will hold at any infinite distance boundary of moduli spaces of quantum gravitational theories, and it links to very interesting concepts together, namely the infinite tower of states and the somewhat mysterious quantum gravity. But before telling you about, what is this pattern all about, let me start by drawing some sorts of motivation so that we make sure that we are all on the same page. So as we all know, whenever we want to describe some physical phenomena at low and low energies, we are doomed to do so in terms of an effective quantum field theory. It typically consists in two pieces, one which is the usual renormalizable piece that contains the kinetic terms, the mass terms, and the scalar potential, and so on. But there's also a second piece, which is usually disregarded, and which frequently contains an infinite amount of higher dimensional and higher derivative operators, which are suppressed by some UV very high energy scale. The UV cut, beyond which our effective description simply breaks down. So, but it's very, very nice, but what about gravity? So should the same story hold here too? Well, the point is that this is the case. As we know, the instant Hilbertons will be considered or regarded just as the first of, in principle, infinite number of higher curvature corrections, which should be suppressed with respect to the former by some sort of, quantum gravity UV cutoff. This is the picture that has been, floating around in the community since the 90s. But let me also stress that very recently, these works from the Harvard group and also a recent paper of us with Alberto and Luis Ibanez, there have been some efforts to try to, study this also systematically in the context of string theory. Just to mention. So, but the question is, well, what is this UV quantum gravity scale beyond which quantum gravitational effects should kick in and should be measurable? The first naive answer that may come to our minds is, given that instant gravitational theory is a non-renormalizable theory with a coupling constant that is dimensional, it has dimensions of energy to some negative power, the naive answer, first answer that comes to our mind would be to precisely take this UV cutoff to be the energy scale associated to the coupling constant, to Newton's constant, which is nothing but the Planck scale. This is actually the picture that was more or less assumed during since the 90s. But as it has come to be appreciated during the last decade or so, it can actually fail. And it can do so in a very dramatic fashion, especially when the number of light degrees of freedom or species that live in our theory grows very large. So in that case, the true quantum gravity scale should be taken as the species scale instead, which was introduced by duality and others some years ago. And I'm showing this expression, the particular expression, at least asymptotic here in this slide. So in particular, notice that whenever this number of species or local degrees of freedom grows very large, the species scale or the quantum gravity scale can become way lighter than our naive expectation, which was a Planck scale. Now, of course, there are a lot of heuristic or semi-heuristic arguments in favor of this scale as the quantum gravity scale. I won't have time to delve into the details. I just mentioned that these arguments typically range from perturbative ones that involve quantum corrections to the self-energy of the graviton, or either non-perturbative black hole physics. But let me stress that this recent picture of trying to actually put the species scale here as the cutoff controlling the EFT expansion in gravity actually reconciles two pictures together, and actually it makes them inevitable. And I would also like to stress that in principle the mere existence of this species scale is good news for phenomenology, for quantum gravity phenomenology indeed. Because it means that in principle one should be able, at least whenever we have some large amount of species, to see these quantum gravity effects kicking way before energy scales of the order of the Planck. Of course, there's a problem here, because as we know in the standard model, just a handful of these light degrees of freedom. So in principle, one would be tempted to conclude that indeed in our 4D universe, this scale is simply too close to the Planck scale, so there's no interesting physics going on. This is just a mere exercise. But here's where the Swampland geese comes to our rescue. So we know that in string theory and more generally in quantum gravity, there are famously no free parameters. And precisely the number of species is such a free parameter. So this means that in principle, this number of light degrees of freedom should be able to change them. And particularly, it can depend on the massless scalars or the depths of the massless scalars of our theories. I try to depict here for the type 2 case. And this is precisely the essence or the content of the distance conjecture. Tells us that whenever we actually probe infinite distance corners of this moduli space, of this space of parameters, there should exist an infinite tower of states, which becomes exponentially light. And of course, this means that for any given fixed cutoff, the number of species or light degrees of freedom grows unboundedly, which implies that the species scale gets parametrically lower with respect to our naive expectation. So the question that we would like to address in this talk will be, well, whether there is any sharp connection between these two ideas, the quantum gravity cutoff and the lightest tower of states, and in particular, whether there is any sort of sharp relation between the decay rates, the slope, the symptotic slope at which they become light at infinity. This is where the pattern enters. So as an outline, I will first present the pattern and also comment further on some of the immediate consequences that follow from it. I will try to, to tell you to explain some very simple examples so that we can get a feel of how this pattern is satisfied and why. And if time allows, I will also comment further on some of the important bottom-up considerations that one should take into account in order to claim finally that the pattern itself is some universal, like truly some universal quantum gravity constraint, and not just a lamppost effect of string theory or whatever. So what is the pattern? So what is this all about? Well, let's assume that we start from some d-dimensional effective field theory weakly coupled to gravity. So that means that our theory includes, of course, the gravitational sector, plus a bunch of scalar fields, some massless scalar fields, phi I, with some funny kinematics controlled by this rank 2 symmetric tensor, which is nothing but the metric of the moduli space. In principle, we could have extra matter, but for our purposes here, it would be enough to just focus on this scalar tensor sector. Now, so in this moduli space, the distance conjecture predicts that there should exist at least one infinite distance boundary where an infinite tower of states becomes asymptotically light in an exponential fashion with respect to the traversed geodesic distance. Now, in practice, whenever we have these multimoduli setups or multidimensional setups, what happens is that there is more than one way to go to infinity. Or in other words, there are more than one asymptotic boundaries or moduli space, and hence one should expect, in principle, different towers becoming light and dominating at each different perturbative corner of the sphere. So what can we do in this setup? Well, it turns out to be useful to define some quantities, some vectors, which are usually referred to as scalar just mass vectors. They are nothing but logarithmic derivatives, or in this case, in the first case, of the mass scale of the tower. And intuitively, they are just vectors in the tangent space of the moduli space, and they point towards the direction, the symptotic direction, in which this tower, the associated tower, becomes lightest the fastest. So if we want to probe some infinite distance limit, determined, for example, by some asymptotic vector t, what we have to do in order to determine which is the tower dominating the spectrum and its asymptotic exponential decay rate, this lambda that I was introducing before, what one has to do is to simply project all the vectors that are appearing, are competing along that direction, and simply choose the one that is the longest. This selects for us the leading or the lightest tower, and also determines its exponential decay rate. And similar considerations can be applied to the species scale. So in particular, one can define some species vectors, which are, again, logarithmic derivatives, and this is the same story essentially follows. So with this, we are now ready to state mathematically what is the pattern that I was telling you about. So it simply tells us that the scalar just mass vector of the lightest or the leading tower of states at any asymptotic corner of the moduli space that we can probe, when taking its inner product with the dominant species scale and that limit, it simply gives a constant, which is nothing but it's only determined by the space-time power theory. Just as simple as that. Perhaps too simple that you may be wondering or asking yourselves first whether it is actually constraining or gives you interesting constraints. And second, whether, well, one should be actually surprised that this kind of relation is satisfied asymptotically or not. So let me try to address these 2 points in turn. So for the first one, I want to claim that indeed this pattern is relation is actually very constraining, and this can be seen in a twofold way. First, there are actually a bunch of like well-known bounds for the exponential decay rates, either for the tower or for the species scale, that automatically follow from it. So I just assume the pattern plus consistency of the picture, of course, and I can retrieve, for example, the sharpened distance conjecture, which is just the statement of that there exists a lower bound for the exponential decay rate of the leading of the lightest tower, which is given by these quantities here. This was actually proposed 1 year ago, and it has been thought of and tested during this last year. And relatedly, one can also obtain, this time, an upper bound for the exponential decay rate of the species scale, which is given actually controlled by the same quantities here, and was proposed by the Harvard group before this year, and it was also argued to hold even in the interior of the moduli space. With an extra mild assumption that it's nevertheless satisfied in all non-string theory examples, one can even recover the species scale distance connector, namely this lower bound here on the exponential decay rate of the species scale, which we proposed a couple of months ago. And notice that these two together already constrain that asymptotically the species scale is forced to decay exponentially. Indeed, it's very constraining, and it's actually more constraining. There's actually more than this, because in practice, whenever you want to check your favorite example, the pattern imposes non-trivial gluing conditions between the different duality frames that one can find in the theory. But this is something that will become more apparent when discussing the example that I was promising to you. Regarding the second point, whether we should be surprised or not, I want to claim that you should be surprised by this fact. And the reason, again, is twofold. First thing is that, well, typically when we determine the species scale associated to just one tower, one can usually find a power relation between the species scale and the mass scale of the tower, which is essentially fixed by the microscopic structure of the tower itself. So whether it's a KK tower, a string tower, or whatever. But this does not fix alone what is the decay rate of any of the 2 quantities. So what are the lambdas? Those, in principle, are free parameters. Well, the pattern actually fixes them completely. And this is something that one can easily realize in the simplest possible setup that one can think of, which is a one modulus example. So in this case, according to the emergence string conjecture, when venturing towards infinite distance points, we can only find 2 possibilities, right? As Rafa was explaining. Either the compactification to a higher dimensional theory or an emerging critical state of your phase. So in the first case, again, as I was telling you, the leading tower of states is given by a KK tower, and one can compute also the species scale taking into account the degeneracy of the states, and it turns out to be nothing but the higher dimensional Planck scale. Now, these 2 quantities are related once you tell me what is the number of internal dimensions that are decompactified. So in principle, there's a power law relation between these 2 quantities. What is not fixed again is the decay rates, in particular this time the scalar access to mass vectors of the species or of the tower. So imposing the pattern actually fixes them to be in precisely these quantities here. And relatedly, well, in the case of the string, is even more remarkable, because since the string scale actually controls both the species scale and the tower scale, the pattern itself already tells you what should be the decay rate. It already fixes it to be 1 over square root of d minus 2. And not surprisingly, or surprisingly enough, depending on your taste, these are all the values that you actually find in every perturbative corner of quantum gravitational theories, except possibly for the compactifications to running solutions, such as the one that Rafa was telling about in the previous talk. And not only that, because there's another reason why you should be surprised. Because in principle, the species scale knows about all the towers, all the states that become light, not just the leading one. So in particular, whenever we have more than one tower, it's not at all obvious that a simple relation between the lightest scalar charge to mass vector and the species scale vector would still hold. And this becomes very apparent whenever we go to multidimensional or multimodular setups, as I'm trying to show you in the next couple of minutes. So imagine that you get a very simple 2 modular example because the two moduli are essentially volume modulus of certain internal cycles of your compactification space. So for the first case, for the compactification space, you actually get one KK tower associated to each cycle. And from it, you can also get the corresponding species scale, namely the higher dimensional time scale. And these two pairs of vectors here, the blue ones that are the scalar Chaston vectors and the species scale one, which are the red ones, these two pairs of vectors, which are collinear, satisfy the pattern themselves individually. The reason is the same that I was telling you about before in the first toy model. What is non-trivial is the pattern to be actually satisfied for any intermediate direction. In order to check this, what one has to do is to, well, fix some direction and try to see which are the states that are contributing to the species counting. And in principle, there should be bound states, or mainly like particles moving with different non-trivial momentum along the two cycles, which can enter into the game, into the computation, and can modify the species counting. And when you take this into account and compute the new species KK3 red that I'm showing you here, which actually lies in the orthogonal locus of the Hall expand by the two previous individual scalar Chaston mass vectors. So this actually is crucial for the pattern to be satisfied between the two leading towers, namely KK1 and KK2, with respect to the dominant species scale within all these range, which is just the highest Planck scale, namely the one associated to the full decompactification. And similar story happens for the second case, for the second scenario, for the merging string limit. I would also like to stress that whenever you're able to draw these kind of diagrams, it is fairly easy to see quickly whether the pattern is satisfied or not, or it's going to fail. Because the mathematical, well, the statement here, the product can be actually related in a one-to-one fashion to the fact that the polytopes, namely the cars that you construct upon joining the different vectors, either for the towers or for the species scale, should be dual to each other. Namely, the vertices of one should be orthogonal to the edges of the other, or vice versa. And this is something that you can really get convinced about in these two simple examples. Okay, so in the pattern, in the paper, we discussed a lot of examples. We prove it for maximally supersymmetric setups, but we also discussed lower dimensional and lower supersymmetric scenarios where strange things can happen, or we get different casuistics. So we gather a lot of evidence in favor of the pattern. If you're interested in this, I really encourage you to go to the paper, choose your favorite example, and see how this pattern is satisfied. But in the interest of time, I will choose possibly the simplest non-trivial example that one can think, which is type 2 string theory on a circle as a premise. But let me phrase it in terms of M theory instead, because this is just the way in which we present it in the paper. So imagine that we take M theory, we compactify it on a two torus, and we get a 9-dimensional maximally supersymmetric gravitational. So in particular, this contains, of course, the graviton plus a bunch of scalar fields, which are nothing but the complex structure and the overall volume of the internal space. These are the moduli fields of our theory. And there are two nice features about these maximally supersymmetric setups in general, which will allow us to do very nice analysis and very neat. Which are first of all that the moduli space is classically exact, so we don't have to worry about further quantum corrections that may modify our conclusions or tensor, if it possible, infinite distance limits. And second, and relatedly, the towers that actually fulfill the distance conjecture are 1/2 BPS. So that means that their masses are actually protected. The expression is classically exact in terms of the moduli, and in particular, this translates into whenever we extract the vectors, they are completely fixed. They don't change upon us moving around the moduli space. So you can actually see it on your favorite moduli space, compute the masses, the vectors, and then the picture that you are going to end up with is not going to change. Okay, so let's do it together. What are the towers here? So there is only a handful of them. There are KK modes, of course, along the internal cycles of the torus. There is also a dual KK tower, which arises from wrapping the M2 rays completely on the torus. They signal the compactification to 10 linear theory. And finally, there are BPS streams, which arise again by wrapping the M2 branes this time over only one cycle of the internal space. So what one can do is to obtain their masses and tensions in terms of the moduli of our theory, then take the log derivatives, extract the relevant vectors, and after turning the crank and doing the maths, I'm not going to bother you with the details. You can draw them in a very nice 2D picture and quickly visualize or check if the pattern is satisfied. So this is the result. This is a very nice picture. So there's a lot of things that one can say about this. First of all, let me just stress that it consists in two triangles. The outer one is constructed out of the scalar access to mass vectors of the towers, so it has to do with the towers themselves. And the inner one corresponds to the species scales among the different things. As you can see, we can divide our our space or our diagram into different local patches, which are perturbative, and where some specific perturbative description it's more suited to the region. And also notice that the strings arise precisely at the edges of the outer triangle and are fixed, so they do not change when plotting the tower or the species scale, as we were saying in the first toy model. But now let's try to see whether the pattern is satisfying or not. So remember that, as I told you, also in the second toy model, this mathematical relation here can be translated univocally into the fact of the two convex hulls, namely the two triangles, being dual to each other. They should be dual to each other with respect to a very particular one sphere, in this case a circle, of radius square root of this quantity here, and which is the circle that I'm showing you in yellow. So let's see whether this is happening or not. First, notice that the outer triangle is completely outside the convex hull is completely outside this sphere, which is the first indication, and the species one is completely inside. So this is the first indication that the pattern it's working on here, and also it's a very neat manifestation of the bounds that we were discussing before, how the bounds are fulfilled here and the relation with the pattern. And also remember that the convex, this duality between the two hulls or the two polytopes was all about having the vertices of each of the polytopes being orthogonal to the edges of the other one, and vice versa. And this is something that, again, you can get readily convinced of by staring at this picture for 10 or 20 seconds. So very nice. The pattern is satisfied here. I don't know how much time do I have left? Probably not that much. But let me try to summarize what is the take home from the bottom-up perspective that we emphasize in the paper. So I will be rather brief. So of course, to claim that this pattern, which is very nice, you can also draw pictures, which is also very nice. To claim that this pattern is actually a universal feature of quantum gravity, one should go beyond string theory. One strategy to do so is, to study from a bottom-up perspective, so trying to see what goes wrong in terms of physics or as much amplitudes, whatever. Otherwise, if it's not satisfied, this is something that we didn't succeed at. But at least we were able to pinpoint what are the minimal requirements or the sufficient conditions that one should explain from the bottom-up perspective to get convinced that this is actually at work in quantum gravity. So I will give you only the upshot of what these conditions mean intuitively, so that you can get a feeling of how when put all together, they ensure that the pattern is actually fulfilled. So the first condition is a condition on continuity of the exponential rates of the lightest hour of states, and also well definition of the product itself. In practice, what this means is that one can, as I was showing in the example, one can actually divide the diagram or the moduli space into different perturbative corners, where each of these corners is actually dominated by one scalar mass vector associated to the leading tower. So in particular, when we cross from one region to the other, there's a change, in this example at least, of the interpretation of the leading tower of states. Within each of these regions, one can argue that the vectors are fixed such that the product is constant. course, this does not guarantee that the constant that one gets at each different region is going to be the same. And for this, we're going to have to ask for another condition. The second condition, which is arguably the most important one, but and the less understood. So the idea is that whenever we have several more than two towers competing along some direction, so whenever we are precisely at these interfaces between two different regions, there should exist bound states involving the relevant towers, such that the species scale that one actually obtains and that dominates that limit precisely points along the direction. And this is something that actually can be seen in this type 2 S1 compactification example. In particular, notice that whenever we move along this direction here, the one that I don't know if you see my pointer, okay. But whenever we move along this direction, we get two competing towers, one which is of cakey nature, another which can be thought of as winding modes. Of course, they're mutually non-local. In principle, they shouldn't talk to each other. But actually, they do, because at this direction, we get the string, which forms bound state between all of them. And a similar story holds here whenever we get the two KK towers competing. We get, actually, as the species scale, the 11 bit bands. So the very fact that we get this situation implies that the product that we get at each region is continuous upon crossing the regions. So so one can argue then that whatever the constant you get in one of the regions, this should be the same over all the other ones. And finally, to set it to 1 over d minus 2, this famous number, one only needs to ask for the existence of at least one of these, the limits of emergent string nature or the compactifications to a higher dimensional vacuum without any defects like the ones that Rafa was talking about. This already sets up the constant to be 1 over d minus 2, and then we can claim pattern insertion. So these are the three minimal ingredients that one should understand from the bottom-up perspective in order to claim full universality of the pattern. So since I'm out of time, probably.
Yes. If you
I
can
will,
finish,
I will leave it here. I will leave it here so you can read yourself the summary and ask the questions if you have.
Okay. Thank you very much for the talk. Are there any questions? Yes, Dieter, please. Dieter, you can go.
Yes, thank you very much. Very nice talk. So actually, I have the following question. Suppose the emergent string conjecture is true, or even if there would be a bottom-up argument for the emergent string conjecture, is what you say, namely this remarkable relation, a consequence of the emergent string conjecture, or do you need more?
A very good question. So we thought a lot about this. I mean, if you look at the emergent string limits, it looks like it's a consequence of the emergent string conjecture. Also, the fact that you can always find, or typically you find the compactification limits also follows from the emergent string conjecture. So naively, one would say, well, one would be tempted to say that it is actually a consequence of the emergent string conjecture if you assume it from the start. I would say so. In the paper we actually discuss this. If you see, like we got three minimal requirements that actually, when put together, make the story hold. If you can explain all of them from the emergent string conjecture, I would claim then that this pattern follows immediately for me. The first one does not come from the emergent string conjecture. It's rather it's another thing. It's a continuity argument. I mean, I didn't have time to really dig into the details of this because one has to take into account all these newly studied limits of the compactifications to running solutions and all these things. All this is taken into account in this condition. The third one, of course, is related to the emergent string conjecture. It's actually weaker, right? We only ask for one of these limits to exist. And the second, in principle, is not directly related to the emergent string conjecture. But actually, if you sort of refine it to say that all the towers that are competing at any limit and that should form bound states should be understood in some duality frame properly, like KK towers, like as having, for example, in the emergence, in these perturbative string limits, then this would follow from the emergence string conjecture. So it's quite related to it. We thought a lot about it. I mean, at the beginning, it looked like it was a consequence of it, but you know, there are some subtleties there that perhaps with a refinement, it could follow immediately.
Okay,
But I
very
should
good.
also say that I should also stress that this also, if you, for example, don't assume the Distance Conjecture, and for some reason you find some bottom-up argument for this pattern, this could also serve as a way of trying to provide bottom-up argumentation in favor of the pattern, because, oh, sorry, of the Distance Conjecture, because of this interconnection between the two. So.
Okay, thanks. Thanks, very nice for a good answer.
Thank you, Michael.
Oh yes, that was an interesting talk. I had a question about the when you did the toy model to 9 dimensions with the type 2A, type 2B, that diagram you just showed with the polytope duality. If you were to do, instead of a T2 compactification of M theory, if you did a cylinder, so there would be a boundary there, then would you get like the heterotic duality? And the next question would be like, if you do, then you get like the Wilson lines and things like that, which gives you a much higher dimensional moduli space. And could you do any non-perturbative?
In the end, if you can relate that compactification to a dual frame, like for example the theoretic string in the strip or whatever, with your Abba-Witten construction, yeah, in the end you can actually, I mean, you can play the same games. This is actually what we did. We also checked as I was telling you, like we checked thoroughly in a lot of examples. One of these compactifications of theory appear through some duality in some duality corner of the theory that we studied here. For example, when you take the theoretic string on a circle, it has rich casuistics depending on how you turn on the Wilson line. So you can actually probe different limits of this sort in an indirect way, and still it holds. So in principle, yes, I mean, either you study directly, but you have to take into account all the duality frames that can appear, or you study it indirectly by starting from any other corner of the duality star. I'm not sure if I answered your question.
Yes, that's good. I think for the particular case of the one-dimensional heterotic string, there's also a matrix representation, which gives you non-perturbative formulation.
Yeah.
Of course, as you keep compactifying, then the theory gets higher and higher dimensional, becomes useless at some point. But in the particular case of one-dimensional compactifications, that's a way you could check it, is looking at the matrix version.
Yeah, I mean, it's true that, I mean, the example that I showed you is it's exact at the classical level. We also took into account the non-perturbative quantum effects. For example, I mean, it's not the same as the setup you're telling me about. But for example, if you go to the hypermultiple moduli space in Calabi-Yau compactifications, there you have a lot of non-perturbative effects coming at play. And I mean, it's not that you get additional information about those effects, but rather you use those effects to argue that still the pattern holds, even at the quantum level. But yeah, I mean, the more ingredients you get, the more difficult it is to actually be sure that you are checking every corner and that the pattern is actually satisfied. But yeah, like, I think it's a very good question. Thank you.
Okay, thanks a lot.